Hey everyone! So today's lesson is a first-hand investigation, and we'll be determining the sulfate content in lawn fertilizers. So the sulfate content of ammonia fertilizers can be analysed using a gravimetric analysis, so using weight to look at how much is in there. And we do this by converting the sulfate in a weighed sample of fertilizer and converting it to barium sulfate, which is a precipitate. A precipitate is an insoluble form, so that means it can be filtered out later. So barium sulfate is a precipitate, so it's highly insoluble, and therefore we can collect it, dry it, and weigh it again to figure out how much sulfate we had in the initial sample. So how do we do this? Step 1, we need to dissolve 100 grams of 1 gram of fertilizer in 500 ml of water. And we do this in a volumetric flask because it's more accurate than using a measuring cylinder or a beaker. Step 2, we then transfer 100 ml of the fertilizer solution we had in the volumetric flask and then put it into a large beaker using a burette. A burette over there gives us a more accurate volume than, say, pouring it out in a measuring cylinder again. We need to acidify this solution that we have put in the beaker using hydrochloric acid, and then we bring it to the boil to make sure that all the fertilizer is dissolved. Next, in step 3, we add 5% weight-to-weight solution of barium chloride into the solution, so then it can form a precipitate of barium sulfate, which you can see here in the cloudiness. We need to make sure it's a complete reaction by making sure we stir it and give it enough time to precipitate out. In step 4, we need to first weigh the filter paper so we know the weight of it, and then filter through the barium sulfate solution through the filter paper to collect all the precipitate. We make sure that we pour it down the stirring rod so it doesn't splash and we don't lose any of our solution. And then we need to wash it to make sure we get rid of any extra soluble items in there. So we wash with several aliquots of hot water, and then we dry the precipitate by taking the filter paper out and drying it. So once it's dry, we can reweigh it because there's no more moisture in it to alter our results. And we dry the filter paper with the barium sulfate on there. From that, we can get the weight minus the filter weight, and therefore it gives us the barium sulfate weight. So in this case, we collected 0.329 grams of dry barium sulfate, so therefore there's no more water in there. And this was in 100 ml of fertilizer solution, with which we added the barium chloride to precipitate out the sulfate. So in the beaker we had number of moles of barium sulfate denoted by N, BaSO4, and this is equal to the mass over the molar mass, so small m over big M. So the mass we collected was up here, 0.329 grams of barium sulfate we collected, and the molar mass is the mass of barium plus sulfate plus 4 oxygen atoms, which is 233.36. So divide those two, and then you'll get the number of moles, which is 1.410 times 10 to the minus 3. Because we had this is the number of moles of barium sulfate, it is also the number of moles of sulfate because we didn't alter anything. So the mass of sulfate in the volumetric flask is equal to the mass of sulfate, MSO4, is equal to the number of moles of sulfate times the molar mass of sulfate. So here we calculated before 1.410 times 10 to the 3 moles of barium sulfate, and then the molar mass of sulfate is 96.06. times it together, and then we get 0.135 grams. So the mass of sulfate in the volumetric flask is 5 times this, because we only took 100 mils out, but we had a total volume before of 500 mils. So we make sure we times by 5. So 5 times the mass we had here, 0.135 grams. 5 times that gives us 0.676 grams. So the sulfate content of the fertilizer in percentages is the weight we just got, 0.675, divided by the total weight of fertilizer we had in the very beginning, which was 1 gram, which we dissolved in 500 mils. So we get 67.5% weight to weight. So the validity of this analysis is dependent on a few assumptions, and one of those is that the precipitation reaction is quantitative. So that means that the filter that we used had collected all the barium sulfate particles. We can't make sure of this, but this is an assumption we make, that it collected everything. We also assumed that there are no other species present in the fertilizer which can react with the barium ions and form a precipitate. If it did, it would give us added weight to our sample and therefore give us a different answer to what we wanted. So we can improve the accuracy of our experiment by A, using an electronic balance rather than a beam balance. An electronic balance is more sensitive and more accurate, and you can even get ones that give you very, very accurate results in smaller than milligrams. We can also use a fine analytical grade quantitative filter paper rather than a normal filter paper. This is finer and allows us to collect more barium sulfate precipitate, and also the smaller pieces of it. If it's too big, the pores, then they'll pass through into the filtrate and then we'll lose it, and that's giving us wrong results. We can also improve our experiment by using a hot solution to prevent occlusions or other species in the barium sulfate precipitate. So using hot solutions will allow us to make sure that everything is mixed together, everything is reacting, and everything is dissolved, and allows the barium ions to then attach to the sulfate. So reliability is really important, and it can improve by repeating our experiment multiple times and then averaging the results. If we only do it once and we make a mistake, then we can't take this as the correct answer. So that's why we need to repeat our experiment. We also need to make sure that the precipitate is thoroughly washed with warm water, so we can then remove any extra soluble species that are not barium sulfate. If we leave it there, then the weight is more than what we expected, and therefore it will give us a wrong result. We also need to make sure we thoroughly dry it, because as I said before, if it's not dry, water is heavy and it will make our sample heavier than what it's meant to be. We can use desiccators, which pull out the water in the air and make sure that it's dried completely. Our filtration must be complete, otherwise the percentage of sulfate will be too low. So if we don't filter everything, we miss out on some sulfate that could be filtered out in our weight. And in order to achieve high accuracy, you can use a pre-weighed filtering crucible. This doesn't use filter paper, and so it's more likely that you're going to get all the barium sulfate. So to recap, what we did today is we looked at the sulfate content in fertilizers by using a technique that makes a precipitate and weighing it. So what we did, we dissolved our ammonia fertilizer in water. We then added barium chloride so the barium ions can attach to and bond to the sulfate and therefore form a precipitate which is insoluble. We can then filter out this insoluble particles and then weigh it again once it's dry to determine how much sulfate was in the initial sample. So we can now go on to some questions. So question 6, we had a 2.45 gram sample of lawn fertilizer as analysed for its sulfate content. We then, after filtering and drying, we get 2.18 grams of barium sulfate, and we need to find out what is the percent weight to weight of sulfate in the lawn fertilizer. So for this question, you should underline the important information, and in this case, you had a total initial sample of 2.45 grams. After we dried and treated it, we get 2.18 grams of barium sulfate, which is also important. And the verb here is what, so we should circle that. And the percent weight to weight, that's what we're looking for. So first of all, we need to figure out the number of moles in the sample. So the number of moles of barium sulfate is equal to the mass, small m, over the molar mass, big M. So the mass we had is up here, 2.18 grams of barium sulfate. And the molar mass of barium sulfate is 233.36. When we divide it, we get 9.342 times 10 to the minus 3 moles. And the number of moles here is also equal to the number of moles of sulfate. Next, we need to determine the mass of sulfate. And this is equal to the number of moles of sulfate times the molar mass in big M. So the number of moles of sulfate we just calculated here. So it's 9.342 times 10 to the minus 3 moles. And then we need to times it by the molar mass, which is 96.06 for sulfate. And what we get is 0.897. So next we need to then determine the percent, because that's what they were asking for, the percent weight to weight of sulfate in the lawn fertilizer. So to get the percent of sulfate, we need to get the mass we just calculated, 0.897, and we need to divide it by our samples, which is 2.45 grams. We then have to times this by 100 to get a percentage, and what we get is 36.6%, which is answer B. Oops. So now we can move on to another calculation question. Question 7. A student weighed out 1 gram of fertilizer and dissolved it in water. 50 mils of 0.25 molar solution of barium chloride was added, and a white precipitate of barium sulfate was formed, which weighed 1.8 grams. So we need to calculate the percentage by mass of sulfate in the fertilizer. So we go through the question again and make sure we underline all the important information. So here the student weighed out 1 gram of fertilizer, which is important for the calculation, and it was dissolved in water. We also need to remember that it was 50 mils of 0.25 molar barium chloride solution was used, and then the barium sulfate that we weighed out is 1.8 grams. We next need to calculate, so that's the verb, and we need to make sure we get the percentage. So how do we do this? First, the number of moles of barium sulfate is equal to the mass over the molar mass. So the mass here, which we weighed out, is 1.8 grams, and then the molar mass of barium sulfate is 233.37 grams. So after we divide it, we then get 77.7 times 10 to the 3 moles. So the number of moles of sulfate is also equal to the number of moles of barium sulfate, because it's the same amount in there. And that is also then equal to the same number, 7.7 times 10 to the minus 3 moles. So to calculate the mass of sulfate, we then times the number of moles that we have times the molar mass of sulfate, and that's 7.7 times 10 to the 3, times that by 96.07, the mass of sulfate, the molar mass of sulfate, sorry, and we get 0.74 grams. So to calculate the percent mass of sulfate in the fertilizer, we then take this mass that we just calculated, 0.74 grams, and divide it by our sample size, which is 1 gram of the fertilizer we used. Times this by 100 because they asked for a percentage, and we get 74%. So we can now, we've just done 2 calculation questions. We can then recap on our previous lesson, which was about AAS. So this question is asking, what are the advantages and disadvantages of AAS? So the verb here is what, and we have to answer 2 parts of the question, which is the advantages, and make sure we also answer the disadvantages of AAS. So firstly, we'll do the advantages. It's a relatively simple technique, as we went over before. It's really just shining a light through a sample and then measuring the absorbance and getting that to give us the concentration of ions in the sample. It's also a very sensitive technique because it can measure the concentration down to parts per billion, and it's relatively inexpensive to operate once you have all the materials. It's also really fast because you just have to put in a sample, vaporize it, and then get the readout straight away. There's no lag time. And it's also really accurate. However, it does have its disadvantages. It has a high initial expense, which is because the equipment, the machine, is really, really expensive. And it only really can test 1 ion at a time, because as we said before, the cathode, the hollow cathode lamp is specific for the ions that we're looking for. So if we want to change it, we need to then change the lamp, and we can't do multiple tests at once then. So we just covered the advantages and disadvantages of AAS, but we'll just go over some more questions on AAS. So question 9 is list some uses of AAS. So AAS we can use in a variety of applications, but the ones we're going to talk about here today is that in industry and in environmental monitoring, we can use AAS to analyze metals and alloys. We can also look at the understanding of effects of trace elements in the body. So we can look at iron, magnesium, and see if it's required for healthy development, if people are sick or deficient, or we can look at crops and livestock. We can also look at the monitoring of the concentration of heavy metals such as lead, mercury, and cadmium in soils, water, and we can also look at it in living tissues because we don't want to be eating too much of these toxic metals. I know that's only 3, but I'm sure you can come up with a lot more. So finally, we can look at question 10. Outline the meaning of quantitative analysis and qualitative analysis. So here we need to make sure we outline, so just tell us what's going on. And we need 2 parts of the question to be answered, quantitative and qualitative. So we need to just describe the difference between the 2. So a qualitative analysis identifies chemicals present in a sample, but it doesn't really give us a specific number. It just tells us a yes or no type of question. A quantitative analysis, however, identifies chemicals in a sample and the percentage of each chemical present. So it gives us a number, and we can then compare these numbers. It gives us like a continuous spectrum rather than a yes or no binary type answer in a qualitative analysis. So to sum up today, what we looked at was how do we figure out how much sulfate is in ammonia sulfate fertilizers, and we used a gravimetric analysis, and the principle behind it is that when we dissolve the ammonia sulfate into water, we can then precipitate out the sulfate by using barium chloride, because barium binds to sulfate and it then causes a precipitate which is insoluble. We can then filter it out, dry it and weigh it, so then we can figure out how much we had initially. And then by doing this and a few calculations, we can then figure out the percent of sulfate inside the fertilizer sample we had initially.